If you followed this channel for any length of time, you know I need a new project like a moose needs a hat rack. But still, let's dive right into it. While doing some inventory of the giant heap of junk that I call my, well, parts store, I found that I had not only one, but two of these small-ish CRTs. These are electrostatically focused, electrostatically deflected. I think, although this one might be magnetically focused, because it came with some yokes. But anyway, these are basically oscilloscope CRTs. This one came out of a Tektronix oscilloscope. It has a Tektronix part number on it. Nice old Tektronix logo. And this one is East German made. But this is very nice because it's a little smaller. The voltages are a lot they're a lot lower. So this is running on moderately high voltage. I think this needs about 1,000 volts tops, which is nice because this is 1,000 volts you can fairly easily generate, and also you can handle without giving yourself all that much grief, although you should still be careful. I mean, it's 1,000 volts, it will kill you, but it's a lot better than generating, I don't know, 20 to 30 kilovolts for a TV CRT. I mean, this Tektronix one over here, it's a little higher in its voltage requirements. This runs off, I've got the schematic of the original driver circuit right here. This runs off about 5,000 volts. So this is a lot harder to drive. Well, this is nice. I also think it looks very, very good. I like the look of this, with the largest socket on the back, the largest base. It's just a nice tube. So what I think I'll do is just make a basic cathode-ray oscilloscope. And what we need is this tube, which is already most of what we need. We need a power supply to drive this, which generates a couple of voltages, like the anode voltage and a couple of focusing voltages and stuff. And then we need amplifiers for the signal, and we need an oscillator that basically generates the sweep that goes across this face. Also, this is a green phosphor tube. It looks very nice. I had this just hooked up to 1,000 volts off my lap power supply, and it generated a couple of voltages here and there, and just got it to display a dot on the screen. So I'll probably, if I can still find it, I'll put a picture here. So I also, that was the purpose of this. I wanted to know if this tube actually works, and it does. So the next thing I did is I made myself a little stand for this. These are just 3D printed sort of pillars here that are screwed down to a wooden base, and they have just some string, and attached to the string there are these small springs that, if you hook them over here, over this bolt, they will give you a little bit of tension without clamping down on the tube too much. So if I assemble this fits in here. And then these just loop over. And slide onto this here. There we go. So this is a nice sort of mount because it doesn't put all that much tension on the glass envelope. And yeah, you can still rotate the tube, but it's all nice and sturdy in here. But you don't want it to clamp down on this with a metal bracket or something, because if the tube heats up and there's about a 3-watt heater going in here to light up the filament to heat the cathode, then this will expand slightly and then you'll crack the glass and you'll send shards of glass everywhere, which is not great. So yeah, this is for the mount. So next thing we need to think about is how to build the power supply. I want to have this project all vacuum tube. So first idea was to just use a large power transformer, and I have one that puts out about 700 volts, and then feed that into a doubler and arrive at something that you could actually use. I don't want to do that for various reasons. First of all, the transformer is really huge, and it would probably, the magnetic field from the transformer would screw with the rotation of the trays and stuff, and I don't necessarily want to do that. Also, I sort of want to save that transformer for another project, because it puts out 700 volts actually at about an amp. And this is way too much for this. I would never need that. I think the high voltage on this will be less than a milliamp. So it's just barbaric overkill. The next thing I thought about is use one of those little flybacks that they had in small portable television sets, and I think this one actually came out of a heart rate monitor, but or a medical device that was attached to the patient, and it had a screen, and it said something about the heart on the back of it. So yeah. So this one actually has a driver transistor on it, but we could just rewind that coil, 3D print a little 3D print one of these plastic things here, and just put more windings on there, because this is supposed to run at like 40 volts, and if you use a vacuum tube, we'd very likely use higher voltages to drive that, so 100 to 200 volts. Have this as the feedback to make it oscillate, and then derive high voltage from this, which is the original high voltage winding, although we could also replace that if we need a lower voltage, because this will probably put out more than a kilovolt. This will probably go up to 7-8, because the CRT was in the same sort of class as the Tektronix one in terms of voltage. So yeah, this is actually an interesting thing, and I might still do that, because that would be really neat. But for the moment, what I'll do, I have a whole box of these. These are small power transformers, 3 volts on the secondary and 230 on the primary. And I have literally boxes and boxes of them. So I might just stack up 2 of those, feed them into a doubler, and feed the primary from 6-7 volts. And that I could also use to heat the filament in the tube. Yeah, that would be probably a neat solution. But I'd still keep the rectifier section that I'm going to build. I want to build it in a way so that if I later down the line decide to use a flyback or go with the big clunking power transformer, that it would still accommodate that. But I'm sort of putting the design center value at about 500 volts input. And so I will definitely need a voltage doubler. And for the voltage doubler, I'll just use 2 of these PY88s. I have boxes of those. These are efficiency diodes out of television receivers, and they're good to about 7 kilovolts reverse, so that's fine. 140 milliamps forward, which is also way more than we need. And you can time together a nice series string. So I'm going to use that for all the tubes and then just connect them up to the mains. Fuse the string. But yeah, that would be a neat solution to that problem. So what I also did is I made myself a little chassis, which is just a piece of sheet metal that I drilled holes into for tube sockets, and this is actually for the top cap connection. So let me just plug that in here. These sockets are a little tight when you first plug a tube into them, but better that way around than being too loose. So when you have the anode cap up here, a wire will come down through that hole. So that's what that's for. And then I also put 2 other holes here. This is for sticking pots through, so you can actually go in with a non-conductive screwdriver and adjust the anode voltage and the focusing voltage and whatnot. The other 2 tube sockets, well, one of them I'm definitely going to use for a regulator, for a gas-filled regulator tube. I'm not sure which one yet. And this one I just put in for symmetry. I might still put a tube there, a sort of regulator tube or something. I'm not sure about that yet. If not, I'll just leave that empty, and that will be fine as well. Or I do something else with some other part of the circuit. But yeah, I'll probably mount that somewhere here later on. Yeah, but now I need to get that voltage doubler built up, and I think I'll do that, and then we'll come back to the project. So next step in this project was to basically put the tubes in here, make a capacitor bank. This is 4 47s at 450, all in series, so I get about half that, around 20 at 800, 1600, which should be plenty enough. And then I've got this temporary transformer arrangement here with 2 of those in series, and I drive the secondary from an 8-volt AC supply, and that gets me up to about 1200 volts on this capacitor bank. This diode capacitor arrangement is just a full bridge voltage doubler. If you look at the circuits online, that will be rather self-evident how that works. I also have this mounted with a couple of largish bolts. I'll just look at the bottom of it here. I've got these capacitors on some, well, it's not Vero board because it doesn't have the copper pads or the strips going across. This is just some FR4 with holes in it, and it's important that you don't have the copper on there if you're doing high voltage work, because then you'll get arcing in between the contacts. I also have a little bleeder resistor on here, which helps with not getting shocked. And while we're at that, on the subject of not getting shocked, if you have that in here, and I unfortunately had to learn this the hard way. Unfortunately I had to learn that, but fortunately enough at that, the bank was discharged to around 100 volts, so it didn't give me more than a little bit of a tingle. These caps, well, the top cap here, this aluminium cap with the vent on it, this is actually connected internally to the negative side, the ground side of the capacitor. And usually that isn't a problem, even if you have a couple of them, because they will be in parallel. And if you were to stick your fingers across, then yeah, you'd be touching ground and ground. But if you have them in series like that, and you actually grab this like this, and you touch both of these things, then yeah, you're touching the negative side of this and the negative side of this. So you've got about 3/4 of the voltage on this bank right across your fingers. And that's what happened to me, and that actually tingled a little. But fortunately, again, the capacitor bank was discharged enough, so I didn't get much of a shock there at all. Albeit this could be quite dangerous if you have discharge up to 1,600 volts. I not want to do that. I think what I'll do is I'll stick some Kapton tape over this very soon, because I always do sort of this high voltage stuff with one hand in my pocket, so you at least can't do this where you're getting it right across your body. The worst you can do is grab it like this, or maybe touch it with your hand, and then you'll get, if you really have it charged up all the way, you'll get a little shock and a little burn, and it will hurt like crazy, but at least you won't die. So when working on this stuff, you should definitely follow all the rules and guidelines to, well, basic rules and guidelines to working with high voltage, even if it's just a prototype setup and that. So best thing to do is just don't touch it while it's powered up. Don't. But this is just the thing with vacuum tube gear. There's high voltages in here. You've got to be careful, and you've just got to know your stuff. Else you're getting shocked. So let's look at this for a second. Let me just grab that out here. This is just the basic multiplier circuit, and I've got these two leads here, which are just feeding in the power for the two filaments inside. And I've got that connected up to what is this? 3.4. Basically, this is out of a fluorescent lamp, and you can put mains on there. I don't think you can put it directly across it for long times, but if you have it in series with a little bit of that, that should be fine. And this is just adding some just adding some impedance to the circuit. So I can actually connect this up to the mains, and I'll drop a lot of voltage on this without dissipating any power. And then I'll have 300 milliamps of AC flowing through these filaments to light them up without having a power transformer of the proper rating, which is just how series string works. Just as you connect them all up in series, and then ideally you would hit your mains voltage. And if not, in the olden days, they would sometimes put a power resistor in to dissipate just the 30 watts or so to the mains voltage. But what we do nowadays a lot, because we have those large non-polarized capacitors for AC applications now, is just put a capacitor in, and that saves yourself some power. So I'll just assemble this here, and I'll put some leads on it so we can actually measure what it's doing. So I made a little measuring setup here, and what I've done, this is unpowered at the moment and unplugged, so it's safe to actually touch it, although I have the leads connected, but I don't have them connected to the power supply on the other side. I've got two 1 meg resistors down here acting as a resistor divider that we can actually measure the voltage, because this only goes up to 1,000 volts. So the actual thing has double the voltage you'll see on here. I've got this connected to the capacitor, which I'll just in a second plug into my Variac supply, and this is set to about 200 volts. to actually light up those filaments here. And then I have those two leads, and they will be connected to an 8-volt power transformer that puts out AC. So let's just plug it all in, and I'll plug in this first. Here we go, and then I'll switch on and plug in the Variac supply, which is this over here. And now I have the Variac on. And now it takes a little time for the vacuum tubes to actually heat up. So just give this about 30 seconds. Then we should actually see the voltage on the multimeter rise. And here we go. The tubes are heating up. And you can't see it on the video, but if you look at them from the side, you can actually see them glowing inside already. So we're about 60 volts, 100, 200, 400, 600, 800, 1000. We're going up to 1200. And now it's slowly tapering off at about 1300. So that is actually sort of the perfect voltage, because that gives us a little wiggle room to the 1000 volts of anode voltage that we need. So we can also derive our negative grid voltage from this, which will be about 100 volts, I think. So this arrangement will do quite nicely. So I think I'll work on the resistor divider that actually provides all those different grid voltages next. So let me just switch this off, and we'll wait for it to discharge so we can actually safely continue on. So with the 2 bleed resistors on there now, it actually discharges quite rapidly. But it's still 500 volts on there. You do not want to touch that. You definitely do not want to touch that. So I'll wait till it's down to about 20 volts or so. At that point, it's still not great to touch it, but if you keep away from the capacitors, you'll be relatively safe. And then you just unplug your mains. So there's no chance of the mains actually. Even if the switch would turn on, there would be no risk of you actually getting the mains across you. So we'll unplug this and unplug this. Alright, now at about 50 volts. Just wait it to go down a little more. So now it's actually safe to basically manipulate the circuit again at 40 volts. You'll feel that, but it won't hurt you. It won't hurt you all that much. So what I want to do, well, at least if it's a capacitor bank, if you've got like 60 volts and the high current supply, it's a whole different story, or AC. But if you just have those capacitors, you're not in much danger, because you will actually discharge this quite fast if you actually stick your fingers across it. So what I'll do next is, I have these strips of turret board here. These are a little larger, and I don't know where I actually got them from, but I think I want to put them over here, like this, and then actually put the resistor divider on there. That will supply all the grids. But I think those are actually a little too long. But the nice thing about these is, if you unscrew this, you can actually pull those out and manipulate them. So I think I'll just take a saw and just cut off the last 3 or 4. Then I'll mount this, and then we'll think about calculating this resistive divider. It's a little later in the evening, but I've finished with this thing. I stuck it down with 4 screws, and then I put my resistors on here, these 4, and then I also mounted the 2 potentiometers for the focus. This one is intensity, and this one is focus. So you can go in there and you can screwdriver around and set it up all, yeah, just the way you want it. And the values that I used for that, I'll just put this on top here, is I've got my 1200 volts coming in, and then I have 2 300k dividers, a 10k for grid free, 40k, then a 50k pot, and then 80k down here. I basically chose those by just roughly dividing it up. And then looking at the data sheet and looking, the anode is supposed to be about 1 kilovolt. This is supposed to be somewhere around 500 to 1000, but should be about half of that. Then this should be 90 to 120 volts. No, I think 60 to 120. I made this adjustable from about 90 to about 110, although I will probably put a higher value pot here sometime in the future, but I don't have a 20k, so that's that. Then I have a 40k here, and then I have the cathode, 50k here for the grid 1 negative voltage, and 80k here. So I initially divided this up into basically 2 halves, saying I have about 500k here and 500k here, and then I divided up those 5k into what I need here, 500k into what I need here, and then I just did some measurement and then I just tweaked it around, and that works because this should be about half of the voltage between here and here, and it's about that. This is actually a little high, but I didn't have any nice old 400 and whatever K resistors to put in here. Yeah, and then from the cathode, I just chose something that would let me adjust the right voltage range. Basically, this should be adjustable from about -40 to 0, and that's just what that does. Although you could use a 20k here just as there, and then you'd be much closer in the range. This goes down way too far. This goes to about -100. But yeah, just if you want to do this, just look at your datasheet values and then plug it into your resistor divider formula, and then you'll get where you want to go. And then put it all on some third board and measure it. Just measure it a couple of times, because the amount of current you draw will change your input voltage. And yeah, but I checked this, and this actually works pretty well. I'll probably put a picture somewhere around here that actually shows the tube lighting up and producing a trace or a dot or whatever. And the thing is, now we have to think about the deflection system. And I'm not entirely sure about how those tubes work yet, but I think basically the difference between the grid 2 plus 4 voltage and the basically deflection electrodes, that is what influences the deflection on the screen. And it's in a sort of non-obvious way, if you don't think about how the tube works. The further you go down, so if this is sitting at 500 and you go down to 400 on the plates, then you'll shift the dot to the left or right, depending on where you are with your on which electrode you are. And then also I'll just grab this little notepad here again. You have 4 electrodes. They look like this, and they're contacted like this. And basically your electron beam is going right in here. So the way you deflect this is if you charge this up like this, and then you put the opposing voltage on there, so it's basically a capacitor that you charge up, then you'll actually deflect in this direction. And if you do it the other way around, say you put negative up here and positive down here, you'll deflect it in this direction, and the resulting vector will be like that. It'll go to that side. And so what I want to do is basically just build a vacuum tube circuit now that creates this opposing sort of voltage. So if the signal is, let's say, positive, it will charge up this positive and charge up this negative in respect to grid 2 and grid 4. So I'm not sure about how I want to go ahead with that, but I'll think a little about it and then I'll probably find a circuit. So we are back on this cathode-ray oscilloscope project, and what I did since the last time is I made a little bit of a wire loom just to keep all the cables in check. And I also used some spare pins from a broken octal socket to connect up to here, and then these, which you can't see properly, these are just from a standard 9 pin, and unfortunately I had to sacrifice this, but I left the right pins to actually drive one of these diodes, so I can use this for a diode. But it's much better to have them connected with these sort of terminals. So, and the next thing is also good, and I'll insert some video. I finally figured out how deflection works, and this is basically you take these leads from the deflection plates, and when you don't want to have deflection, you connect them up to grid 2 and 4, and then you have to charge them negative by about 30 to 40 volts to get all across the screen. At least you have to do it with 1, so I guess if you drive them differentially, you have to do 20. And I think the best way to do this would actually be a long-tailed pair with double triode. Like, do I have a double triode? Yes, like this. This ECC83 double triode. Then just have 2, one driving the horizontal and one driving the vertical, and a long-tailed pair, and that will sort of split up the phases. I'll do a little doodle here. Just shift this up here for a second. And what we want to do is basically have the triode here, the double triode. And then have the grids coming in. Have the grids coming in here. like this, and cathode, so we don't care about that for the moment. So we'll have the plates here, and 2 resistors. This goes out to 1, and I'll draw this a little higher. This is actually on camera, yes. No, I didn't draw it a little higher, but so this comes out here. These two, they are connected to grid 2 plus grid 4. And then, and there's being some high resistance, I don't know, 100k or so. And so whenever this is not conducting, there is no deflection, because there's no current flowing here. So the voltage is basically equal here to this point. But then once we draw current here, we'll actually lower the voltage here and therefore drive the plates. And we'll do this in a, I'm going to draw that much nicer later, but we're going to do this in a long-tailed pair fashion. So whenever this goes down, this will go up, and the other way around. So you can actually have that differential drive that we need to drive this tube. And that's, I think, what I'll prototype next, and then we'll see if that works. I think this is a good point to end part 1 of this video while I figure out how deflection works and how to go on from this point, because I think it's time that I actually look at some vacuum tube oscilloscope schematics, which I haven't done yet, and see how they do things. But let's look at what we did so far. We've got ourselves a transformer that produces about 500 volts, that feeds into a doubler circuit, that charges our capacitor bank that we have here, and then we feed that into a voltage divider that provides all the voltages that we need, and that is about 1000 volts for the anode, about 500 volts for grid 2 and grid 4. In practice, this is actually a little higher. This is at about 1200. At the moment, this is about 600, 700. Then we've got our grid 3 voltage, which is variable with a potentiometer from about, I think, 90 volts over this point to about 110, I think. It's probably not enough. I probably have to put a larger pot here, but I don't have any 20k pots, so I ordered some. Then we've got our cathode voltage, and we've got our grid 1 voltage, which is below the cathode. We can also vary that, and that controls the intensity, that controls the focus. So this is where we are, and the next thing I'll do is I'll get out my little breadboard here, and I'll probably develop some sort of circuit to drive the deflection plates, which are, I'll just try and draw CRT here. And we've got the filament here. And we need to think about how we drive this, because this is not series string drivable, so I'll probably have to put another transistor on there. And then we have our cathode, that actually connects to K down here. And then we've got our various grids. We've got our anode here. This is A. And then we also have these deflection plates here. Well, these are obviously on opposite sides. So these are, if these would be pointing like this, then these would be like this, so into the paper. But we need to figure out how to drive these, and I think how you do that is you connect them to a fairly high voltage, and then if you drop them down to a low voltage, they will actually deflect. And I actually tried that with a lab power supply, and that seemed to work, but I'm still not entirely certain how to do this. And I think this will be the subject of the next video, the deflection circuit.